After the 5th of January 1975, when the bulk ore carrier Lake Illawarra tragically collided with the Tasman Bridge, causing 3 spans to collapse. The effects of the collapse were catastrophic. However, the federal government accepted that rebuilding the Tasman Bridge was not enough. Like the Tasmanian government, it agreed that Hobart should never again be allowed to run the risk of losing its only road link between Western and Eastern Hobart.
In March 1980, joint venturers Leighton Contractors Proprietary Limited and Kandak Limited were named successful tenderers for the construction of the second Hobart Bridge. In October that year, fulfilling the commitment made by the previous Whitlam government, the then Prime Minister Malcolm Fraser officially named the future bridge.
Lieutenant John Bowen, at the rare old age of 23, was appointed to form a settlement at Risdon Cove by Governor King, Governor of the colony of New South Wales. And so, ladies and gentlemen, Michael Barnard, in a moment I'll have very great pleasure in unveiling the plaque to commemorate the commencement of the work of the bridge, and in so doing, name the future bridge as Tasmania's Bowen Bridge.
The contractors, Leighton Kandak, were no strangers to the task ahead of them, but the building of a major bridge across Hobart's Derwent River held challenges unique in Australia. Here, in the latitude of the roaring 40s, high winds and low temperatures dominate winter weather. It was partly these difficult conditions which made the building of the second bridge so important to the community of Hobart. And part of the challenge meant the bridge had to be able to withstand an impact from any vessel likely to pass under it in the foreseeable future. To some extent, this factor dictated the choice of the Dowsings Point site, where the bridge would be built just upstream of the temporary Bailey Bridge, erected after the Tasman collapse. Detailed planning had begun in 1975, when the Joint Committee on Second Hobart Bridge was formed, with representatives of Commonwealth and state governments to supervise the project, which was fully funded by the Commonwealth Government. In addition to its overall responsibility of planning and supervision, the Joint Committee chose the name Bowen to commemorate the first European settlement of Tasmania in 1803 by Lieutenant John Bowen. In planning, tunnel and vehicular ferry facilities were considered, along with 17 sites. The Dowsings Point site was chosen because it provided good, though deep, foundations, where the bridge could be built at a moderate cost. It was also upstream of ocean-going shipping, and the largest vessels likely to pass were 5,000-ton newsprint barges. The design allowed for further strengthening to withstand collisions from 10,000-ton barges. The Maunsell and Partners design was a pre-stressed concrete box girder bridge using match-cast segmental cantilever construction. The bridge was built on 9 piers, each standing on a massive foundation keyed into the bedrock far below the river's surface. Between these piers are the 109-metre spans, which carry the roadways, telecom cables, power and water mains across the Derwent. Work first began to develop the roadway cutting on the western shore, to eventually link the bridge with existing roads and the Brooker Highway. Tasmania's Department of Main Roads undertook the roadway construction and improvements. In the river, the bridge piers were built inside huge concrete tubes, coffer dams, which were prefabricated in ring-shaped sections, coffer rings. Below the chilly Derwent waters, silt lays up to 40 metres deep, and beneath the silt is the bedrock on which the piers stand. At each of the river pier positions, test holes were drilled to establish the shape of the bedrock. The base of the bottom coffer ring was cast to match the rock profile. Steel hexagonal jackets secured with pin piles were used to locate the coffer rings, which at first were suspended from hanging trusses on the jacket. The cofferdams, designed by Leighton Kandak, were built in sections in the concrete casting yard at Wilkinson's Point. Each was about 300 tonnes and stood 7.3 metres in height. Wilkinson's Point was like a small city throughout the months of casting, not only of the cofferdams, but of the box girder and superstructure segments. For most of the project duration, it maintained the bulk of the workforce and operated in close association with work on the river to ensure constant activity at two locations. Pre-casting had to be simultaneous with the building of the river piers. All materials from Wilkinson's Point were moved downriver, in many instances, such as the lifting of coffer rings by the crane barge LC1. Once on the site, the coffer rings were stacked one on another, and the whole assembly descended through the water and silt towards its final position on the bedrock. The bottom coffer ring has an extra wide base to clear a path through the silt. And when gravity alone was inadequate for the task, it was helped by jacks mounted on the hexagonal jacket. As they were added, the coffer rings were stressed together and grouted, so when all was ready, they would provide a dry environment for the construction of the pier shaft itself. The cofferdam was complete when it extended from the bedrock to the surface. At one pier, Pier 2, a height of nearly 50 metres, the same height as Hobart's Rest Point Casino Tower. The most intense periods of work on the water came with the pouring of the massive concrete tremie plugs. Every detail was carefully planned and double-checked.
Yes, Carl. Here's Roger.
How are you, mate? Everything okay?
Carl, are we all right for tomorrow?
Yeah.
Everything arranged?
Yeah, all set up. We're ready.
No, remember we want 24 trucks, 22 minimum, 2 spares. But I'll give you a call between 5 and 15 in the morning.
Right.
And you get the trucks rolling, 5:30, let's get them rolling from Flagstaff Gully. 5:45, start dispatching them from Moona.
Right.
They've got to go where they're told and they have to obey our orders. There'll be a two-way radio check on the road going into conveyors. They have to obey us, otherwise they're going to have a head-on. The last thing we want is a head-on.
In this exercise, an unreinforced tremie plug of up to 850 cubic metres of concrete was placed underwater in the base of each cylinder. This effectively sealed the cofferdam. The tremie plugs form the bases for each river pier, transmitting foundation forces to the rock beneath. 2 barges were used to move 24 concrete trucks onto the river, 6 at a time. Concrete was poured at the rate of up to 50 cubic metres an hour.
John Crossan, Jim Needs, John Crossan. Yeah, Jimmy. Would you ask the testers on the Bowen to check that concrete for slump? There seems to be a bit dry at the present moment. I'll put you through to Ken Westing, Jimmy.
It was a long process, through day and night.
I asked them to lift them only the 500 mils, and they lifted them a metre and a bit more, eh?
Roger, Jim. I'll check it out for you. Do you want to check the levels? Could you send Andy around, please?
Check the levels, and I told the fellas on the Tremmy tubes that to lift them 500, but I've lifted them a bit more to a metre and a bit more.
I'll tell them to place them back down to the level, Jimmy, back down to 500 and check the levels again, eh?
Will do, John.
Roger, Jim. I'll check up with you later on, mate.
While marine work continued, there was ongoing activity at Wilkinson's Point. Here, about 150 men, represented by 8 major unions, were on site for the prefabricating of most of the bridge's major components. On the eastern shore, a special bay was dredged to allow for the erection of the central decking unit on Pier 9. It was a milestone in the construction process, demanding and testing planning, ingenuity, and heavy engineering systems. All proved adequate. On the river, the strength of the Tremmy plugs was checked by drilling core samples. With the samples approved, pressure relief holes were drilled through the Tremmy plug and down into the bedrock, and divers implanted piezometers to monitor upward pressure on the plugs. This is essential before dewatering can take place to avoid the build-up of potentially unstable hydrostatic forces beneath the Tremmy plugs. Water which seeped in through the relief holes was constantly pumped out, while more holes were drilled around the perimeter of the plug. Reinforcing steel was grouted into these holes in readiness for the next major phase of the construction. The pier shaft, with its 1,200mm thick reinforced wall, was poured in the annulus formed by the cofferdam on the outside and a cylindrical slip form inside. The form was slowly raised from the tremie plug during a continuous pour. On its way downriver, the first of 14 precast caisson cap noses to be fitted on the river piers, a key safety feature of the Bowen Bridge design criteria. The boat-shaped cap was designed to deflect errant vessels, or at worst, in the event of a severe impact at an acute angle, break off, saving the pier itself from damage. With a temporary support frame in place on the capped pier, it was time for a delicate job. As with all firsts on the construction, this one tested planning and casting accuracy and attracted keen interest. A perfect fit. Concrete skirts to be fitted to low water level will give added protection and a more pleasing appearance. With the caisson cap work complete, the columns to support the bridge superstructure were then poured in situ. With underwater work complete and the pier column construction well in hand, the erection of the superstructure took the critical path. This operation made the Bowen Bridge unique in Australian engineering. The 5 central segments which stand above each pier were pre-assembled, glued and stressed together in the casting yard, transported to the pier on which they stand and lifted into position on the pier column. At 300 tons, this was one of the biggest single lifts in the construction of the bridge, and one which was done with absolute precision. The bridge superstructure, which expands and contracts according to temperature, has to be free to move. This was achieved by setting it on huge roller bearings which move to and fro on their own bearing plates on top of the columns. The lifting of gantry cranes onto the pierhead segments. These cranes lifted successive segments into place, putting them at either end of the growing structure so that it was never more than one segment out of balance. This was the balanced cantilever mentioned in the bridge's design specifications, developed in Europe and used for the first time in Australia on the Bowen Bridge.
About another 3 metres so we can get the hook perpendicular, please. Makes it easy to get in. Yeah, roger, Don. Can you tell me when to stop? Righto, Brian, hold it there. Yeah, roger, got that.
The process enabled the bridge to be built with precast segments of twin box concrete sections, varying in depth from 5.8 metres at a pier to 2.4 metres at each mid-span section.
Yeah, Brian, as soon as the flames are down on the barge, you can hit back up to the point with it. Eddie's got another one there coming down the track now. We'll put it straight in the barge and it'll come straight back down river. Yeah, roger, Cole.
594 segments were precast on 3 long-line casting beds at Wilkinson's Point in the sequence of their final assembly. As each segment was lifted into position, it was glued to the previous one with a 2-part epoxy resin, imported from Switzerland for the project. Temporary stressing bars were used above and below. Later, these were replaced by steel cables fitted in ducts running through the segments. The balanced cantilever construction method is graphically illustrated by time-lapse photography. "37 months after the exchange of letters of agreement, the last segment of the downstream carriageway was fitted and the Derwent was bridged.
Well, congratulations, man. Thank you, sir. Great day. Yes, good to see it all open.
It was a moment of satisfaction for contractor, bridge authority and consultant. With a multitude of steel cables tensioned, tying segment to segment and half-span to half-span, shuttering was lifted into place and the mid-span joints were poured to complete the decking structure. The bridge carries more than just motor vehicles. Water mains were fitted within the superstructure using a specially designed self-powered trolley. Roadworks, light standards, railings, footpaths and signs completed the bridge. All roadworks were completed on schedule, and possibly the most impressive of these are the 4-lane approach road on the western shore, linking the Bowen Bridge to the Brooker Highway, the main route to the city southwards and to northern Tasmania, and the approaches on the eastern shore, linking with the East Derwent Highway.
This bridge is indeed a triumph for Australian enterprise. It is, I believe, a symbol of confidence and progress. It is a step into the future for Tasmania, for Australia. For all those reasons, the Premier, distinguished guests and ladies and gentlemen, I have great pleasure in declaring the Bowen Bridge officially open.
Few who travel here will be conscious of the finely engineered structure below water level. A hidden structure, almost equal in mass to the visible one, which most of us will identify as the Bowen Bridge.